Before we go to the next section, I want to thank our sponsor, Voxel 51, for sponsoring the Best Paper Award, Best Poster Award, Best Open Source Award, and Best Speaker Award. Yes, so next we will go into the IROS Best Paper Candidate session. There are 4 exciting papers where, if I can find the introduction slide. The first will be Tianxing. Do you want to come set up your? He is a first-year Ph.D. at the MMLab at the HKU, supervised by Professor Ping Luo. His research focused on embodied AI, including robotic foundation models, generalizable manipulation policies, and robot data synthesizers. So you have 15 minutes in total, so you can see how much time you want to spend on before it's the question.
Hello everyone, I'm Tianxing, the lead author of RoboTwin 2, and it's our great honor to be selected as the candidate and give an oral presentation here. Now, I'm Tianxing, and I'm a first-year PhD student at HKU MMLab, and my research interest includes simulation, bimanual, and texture manipulation. So, inspired by successful experience at the multi-modality large language model field, we are pay more attention on data to reach embodied AI. So we also propose the data pyramid of the embodied AI. From bottom to the top of the pyramid are the internet data, simulated data, real data, and some special data like tactile manipulation. So, but it's always a very hard question to answer how to also collect simulation data. There are some approaches proposed to do so, like reinforced learning. We can train an RL agent to auto collect data in simulation. But this also suffers from the sparsity rule problem and the rule design problem. For MMLab, you also need human in the loop, the data collection. So this is our goal. That's the reason why we propose RoboTwin. First of all, we do really believe that simulation data can empower real-world manipulation. So we want to propose a pipeline that can automatically collect high quality and diverse expert demonstration data for bimanual robotic manipulation and solving data bottleneck. And to achieve this goal, we have to solve several questions. First of all, how to synthesize real manipulation data in the simulation. So we divide it into 3 steps. First, we do a real-to-sim transfer. Then we leverage MLM knowledge for expert code generation. Finally, we just execute expert code for data collection. And the first time, different from the real world, we need digital assets in the simulation. So at the first time, we empowered by the current day's very powerful 3D AI model, we can do a real-to-sim transfer by just given a single view image. For example, this camera image was captured by my phone and just
Simon, your mic is muted.
The simulation across the no matter the geometry, the surface normal, the rough frame, and appearance. So with this pipeline, we can collect large-scale 2D image data from the internet and just using your mobile phone in the daily life, we can obtain a large-scale digital assets like. And let's after we have this digital assets, we are now thinking about how to push it further. Let's give grasping behavior as an example. All grasping can be represented, especially for the paper, we can represent it by a grasping point and a grasping direction. So if we annotated all objects with this annotation, we can just manipulate it in a uniform way. So the uniform sense, we can annotate every object with diverse and multiple annotation, including some functional points, functional direction, manipulation, grasping direction or and so on. So cooperating with these annotations, we define a large-scale API library for our autodidact lesson. Especially in the simulation, you can just take grasping behavior as an example. If you use a grasp function, just given the object ID, you can directly retrieve the object position in the simulation and also get its grasping point and grasping direction. So you can uniformly manipulate all objects in the uniform way. So here is an example how we do this to do the expert code generation via the MMLab. For example, I want to synthesize data. We want robot to grasp the ball and over it down. So we just give it the NLM prompt about using the natural language description about the task, and also give the agent the API library and also the functional example. The code agent might directly generate a series of code, each line of code representing a retrieving API, and each API representing a primitive skill. So we can directly execute the code. And maybe you have the running log. It's obviously that maybe the success rate cannot be that high because the MLI is not perfect. So we are trying to refine the code. So of course we will have some keyframes captured in the simulation. And the VR agent directly observe the keyframes and find that after executing one line of code, the block was right. So the VR agent might think about what can we refine the code to achieve a better result. So the VR agent will give a log to the code agent, and the code agent will refine the code like on the parameter or achieve a better API, and maybe we can have a higher success rate. And the whole pipeline, we human just need to give a task language description in the natural language. So after synthesizing the data, we are now solving the second problem: how to improve the diversity of the manipulation data. Here is the RoboTwin one. We propose a 75 million task with all collected on the intrinsic scene. And it's obviously that it's hard to claim that this data can directly do a very great thing to real performance. So our motivation is that our policy trained on RoboTwin 2 data can generalize well to the diverse real scenarios. So first of all, we propose a domain generalization across 5 dimensions. We support large-scale diverse objects data collection. We support diverse skills and tasks, and also support different embodiments of data collection. And the first time, with that powerful free AIGC pipeline, we propose RoboTwin object dataset RoboTwin OD, includes 147 categories and 731 objects. Each object is annotated with rich annotations across the manipulation and schematic information. And also, all our annotations are around the objects, so it's obviously that we can do a cross-embodiment data collection. But during our implementation, we find that there are some issues that we need to treat. For example, take grasping a can as an example. A front-end robot might prefer to grasp it from top to the down, but Piper might prefer to do it from the side. So it's our observation that with different embodiment, we completing a task, the strategy of completing tasks may be different. So we propose several ways to tackle this problem. For example, for each object, we annotate it with multiple manipulation annotations. Also, we annotate each embodiment with embodiment and reference because, for example, we just hint the system that a front end might prefer to do a completion task from the top to the down. And we randomize manipulation chunks to ensure a wider range of planning. And finally, we use robot for plan planning for the faster data management. And finally, and then we propose a domain normalization method. We do domain normalization across scene cluster, table height, lightning, background variation, and trajectory level diverse language instructions. With this highly domain normalized data, we can do a very great real scene to real performance. And with those pipelines, we propose a 15 bi-manual tasks with also tests supporting domain normalization. All tasks are support different embodiment for data collection. And we also open source over 100,000 trajectories, manipulation trajectories across the 5 different embodiments. And then we also build a RoboTwin benchmark across the 15 tasks around the easy and hard tool setting, and evaluate different policy performance on the RoboTwin benchmark, especially like RBT type 0. and some imitation learning policy. Okay. Here at our experiment section, we want to realize RoboTwin across three key aspects. And you just skip it. On expert code data generation success rate, we have a 10.9% improvement, and we can do a better performance on different embodiment collection. And in this experiment, we can find that RoboTwin data can improve the generalization and robustness across around for the object for the policy. And in the real world experiment, we find that only with the real world data, performance are only 9%, and RoboTwin 2 data can do a zero-shot performance on like 29.5%, and with only the 10 real world data, our performance can do 42% in a higher setting on the untrained unseen background and cloud scene. This highlighting that our simulation data can empower real world manipulation across the generalization and robustness. Our RoboTwin has published version accepted as the ECCV Mass Workshop Best Paper, and RoboTwin 1 was accepted to the CUTR highlight, and over 1,000 people has participated in our challenges. And we open source our data set on Hugging Face and received 15,000 downloads. We open source our leaderboard. We open source our GitHub code and have 1,600 GitHub stars and 200 frogs, and we have a detailed document and our community of over 1,000 people. And that's our presentation. Thank you very much.
If we have any questions from this class, yeah, we will take one question from the audience.
Thank you.